On Monday the 25th of May 2026, a thermometer at one of the oldest weather stations in Britain read 34.8 degrees Celsius. 24 hours later, it read 35.1. In 2 days, a record that had stood at Kew Gardens for over 80 years, since the 1920s, fell by more than 2 full degrees Celsius. And on the second day, the reading also broke the same station's previous all-time June maximum from 1976. In late May, the United Kingdom posted a temperature that nearly 50 years of subsequent Junies had not been able to match. A senior climate scientist at Maynooth University in Ireland told CNN, on the record, that the data was mind-bogglingly crazy. Phrases like that, from people like that, in places like that, do not appear in normal climate communication. They appear when something has just happened that the discipline did not plan for. And here is the part that should make every American watching this stop scrolling. A new Penn State chamber study has measured the actual temperature at which the human body simply runs out of cooling capacity, and the projection at 2 degrees of warming, on the trajectory we are currently on, puts most of the eastern half of the United States inside that envelope. Houston, New Orleans, Memphis, Atlanta, Washington, New York, all inside it. So how close are we? What does the science actually say? And what happens to the grid the day the threshold is crossed in a major American city? If this is the kind of analysis you want more of, hit that subscribe button and the like. It tells the algorithm to keep showing you these deep dives instead of burying them. Drop a comment with where you're watching from and how the heat felt where you are during the last week of May. Share this with someone who is going to have to live through the next 20 years of these events with you. You're going to want to be here for what the science is actually saying. Now, let's get into it. Part 1. The record that wasn't supposed to fall for 80 years. There is a small instrumental station on the south bank of the River Thames, in the southwest of London, attached to one of the most famous botanical gardens in the world. The Royal Botanic Gardens at Kew has been recording weather more or less continuously since the 1840s. Generations of British meteorologists have walked past the same Stevenson screen, written down the same daily maximum and minimum temperatures by hand, and entered them into one of the longest continuous instrumental records anywhere in the British Isles. The station is not on the top of a mountain, it is not in a desert. It is in a leafy corner of an Atlantic island nation whose entire warm season climate is moderated by a cold ocean, and a maritime polar air mass that, for most of recorded weather history, has kept this country famously temperate. When you live in Britain, the joke about the weather is that the warmest summer day of the year usually arrives with 2 clouds and a complaint. That is the climate. On Monday, the 25th of May, 2026, the thermometer at Kew Gardens read 34.8 degrees Celsius, that is 94.6 degrees Fahrenheit. And the previous all-time British record for the month of May, set in 1922 and matched in 1944, had been 32.8 degrees Celsius. So on a single afternoon at the end of May, before the calendar had even rolled over into meteorological summer, a record that had stood, jointly held, for the better part of a century just got broken by exactly 2 full degrees. 2 degrees Celsius. Not a tenth of a degree, not half a degree, a full 2. Now, if you are not a climatologist, that number might not mean anything to you. Let me put it in context. When monthly temperature records fall at long-term British stations, they usually fall by tenths of a degree. The instrumental record at Kew has been kept since the era of horse-drawn carriages. The kinds of records that fall at sites like that, in countries like that, do not move in 2-degree leaps. They move in fractions. They get nudged. The May 25th, 2026 reading was not a nudge. It was a shove. And the next day, it happened again. 24 hours later, on Tuesday the 26th, the same station, the same thermometer, the same instrument screen, the same patch of grass that has been measured for 180 years, recorded 35.1 degrees Celsius, 95.2 degrees Fahrenheit. The brand new May record that had been set the previous afternoon was broken again by another 0.3 of a degree, 24 hours later. The combined 2-day jump above the old 80-year record was over 2.3 degrees Celsius, roughly 4 full degrees Fahrenheit, above a record that had stood since the early 1920s, and I have to slow down on the 35.1 number itself for a moment, because that figure has a second meaning that most of the headlines did not pick up on. Kew Gardens has, of course, also been keeping a June record. June is the first month of meteorological summer. The previous all-time June maximum at Kew Gardens was set in 1976, during a summer so hot it has its own name in British meteorological history. The Kew Gardens June record stood from 1976 all the way until 2026. The May 26th, 2026 reading of 35.1 degrees Celsius beat that 50-year-old June record too, by 0.5 of a degree. So the United Kingdom, in late May 2026, recorded a temperature at one of its oldest and most respected weather stations that nearly 50 years of subsequent Junes had not been able to match. The reading was on the calendar of May. It belonged to the climatology of July. I want to be very honest with you about how unusual that is. Records like that do not break. They get broken occasionally, by small amounts, after long intervals. When they break by large amounts, on consecutive days, in calendar positions where they should not be breaking at all, climatologists notice. And when senior climate scientists notice, the words they use start to drift outside the normal vocabulary of meteorological understatement. Peter Thorne is the director of the Icarus Climate Research Centre at Maynooth University in Ireland. He is the kind of researcher whose job is to talk about climate signals in calm, measured, peer-reviewed sentences. When CNN asked him about the British and French records that had just been set in late May 2026, the phrase he used on the record was mind-bogglingly crazy. That is the verbatim quote. From a senior climate scientist about a temperature record at Kew Gardens. I will tell you what that phrase tells me, and you can decide what it tells you. Senior climate scientists from European institutions are not in the habit of using words like mind-bogglingly crazy in interviews with major American newspapers and television networks. That kind of language, from that kind of source, in that kind of outlet, is what happens when the data has stopped fitting inside the box that the discipline normally uses to describe it. It is the language of someone who has just watched a record that should have moved a few tenths of a degree, get rewritten by 2 full degrees on 2 consecutive days in a country that should not be doing that in May. So that is the headline data point. But headlines are anchors, not stories. The story is everything around the number. So let me walk you through what was happening in the atmosphere that produced this record, because the synoptic setup matters for understanding why this is not just a freak event. It is a freak event sitting on top of a slowly shifting baseline, and the difference between those two framings is the entire reason we're talking about this video the way we are. The synoptic driver in the language of atmospheric science was a massive and persistent high-pressure ridge that anchored itself over Western and Central Europe during the final week of May. A ridge of that scale in that position, in late May, in a normal year, would be a moderately warm late spring pattern. Maybe a few days of pleasant weather in the south of England, with some uncomfortable afternoons in Paris and Madrid. What happened in the final week of May 2026 was different in a specific way. The ridge did not move, it got stuck. And what gets stuck under a slow, moving ridge in the boreal late spring, with a tropical continental air mass advected up from the Saharan source region in North Africa, is a heat dome. The same physical structure that gave the Pacific Northwest its catastrophic late June 2021 event. The same structure that has been parking over the central United States with increasing frequency in the last decade. The same structure on different sides of the world, producing increasingly extreme heat events at increasingly unusual times of year. The mechanism is straightforward enough. Air sinks under a high-pressure ridge. Sinking air compresses. Compressing air heats up. That is adiabatic heating. The compressed, heated, drying air mass at the surface produces clear skies. Clear skies let in direct solar insolation. The land warms up. The warm land radiates heat back into the air heats up more. Without cloud cover to interrupt the cycle, and without a frontal system or a trough or any other large-scale disturbance to ventilate the dome out and replace the air mass with cooler maritime air, the surface temperature climbs day after day, anchored to a single, slowly amplifying pattern. The ridge sits and the surface bakes. In 1922, when the previous Kew Gardens May record was set, exactly this kind of ridge could anchor over Western Europe and produce a hot late May day. In 1944, when the record was tied, exactly the same kind of synoptic configuration could produce exactly the same kind of event. The synoptic ingredients have always existed. Ridges over Europe in May are not new. What is new is the baseline the ridge is now working against. In 1922, the global mean surface temperature was roughly 0.2 degrees Celsius above the pre-industrial reference. In 1944, it was around 0.4 degrees above. In 2026, the global mean surface temperature, depending on which dataset you use, is somewhere between 1.3 and 1.5 degrees Celsius above the same pre-industrial baseline. That means the air mass the ridge was working with in 2026 is, on average, more than a full degree Celsius warmer at the source than the same kind of air mass would have been a century ago. The synoptic engine is the same engine. The fuel it is burning is hotter. That is why the British Met Office did something unusual when they released the official record statement. They did not just confirm the new daily numbers and post them in the climatological record. They also released a research note in the Royal Meteorological Society's journal Weather that ran a formal attribution analysis on the event. And the result of that analysis, in plain English, is this. Breaking the 32.8 degrees Celsius UK-made temperature record in the present climate is approximately 3 times more likely than it would have been in a counterfactual climate without human-caused greenhouse gas emissions. In return period terms, which is just the statistical language climate scientists use for saying how often you should expect a particular event, an event of this magnitude has moved from approximately 1 in 100 years to approximately 1 in 33 years. So what was, in the climate of the early 20th century, a record event you might see once in a typical lifetime, is now an event you should expect to see approximately once in a working career. And let me draw out what that means in human terms, because the abstract statistical framing buries the implication. A person born in the United Kingdom in 1922 would have lived through one event of this magnitude somewhere in their lifetime, and probably never have seen another one. A person born in the United Kingdom in 2026 should expect to live through several events of this magnitude. Not one, several. The structural relationship between a typical human lifespan and an event that the climate system can produce has shifted in this country by approximately 1 order of magnitude over the course of about a century. That is the attribution science result. That is the official British government statement, peer-reviewed and published. That is not a campaign group press release. That is the Met Office in the Royal Meteorological Society's journal, telling the country exactly how much the dice have been weighted. I want to flag something about the framing that climate scientists use when they talk about events like this, because it tends to be misunderstood. The Met Office did not say climate change caused the May 2026 heatwave. They said climate change made the event approximately 3 times more likely. That is a specific kind of claim, and it has a specific kind of evidential basis. The synoptic ingredients, the ridge, the North African air mass, the clear skies, the strong sunshine, those are weather. They have always existed. They will continue to exist. What has changed is the baseline the weather is working on. The Met Office framed the role of climate change explicitly as amplification, not causation. The atmosphere did not need to be re-engineered. It just needed to be warmed by 1.5 degrees on average at the source. That is enough. That by itself was enough to take a record that had stood for 80 years and break it by 2 degrees on 2 consecutive days. And I want to be careful with you here. I'm not telling you this to alarm you. I'm telling you this because the actual data from the actual long-term instrumental record of one of the oldest weather stations in the world is doing something that nobody planned for. And senior climate scientists are using the kind of language that suggests they did not plan for it either. Whatever you think about climate as a political subject, whatever you think about the policy debates around it, the thermometer at Kew Gardens does not care about any of that. It just reads what is in front of it. And what was in front of it on those 2 consecutive days in late May 2026 was a heat anomaly that the previous 180 years of British meteorology had not seen. The question that the rest of this video is going to ask is what happens next, not next year, not next decade. But what happens to the human body, in the cities and countries where most people on this planet actually live, when this kind of pattern stops being a 1 in 100-year event and becomes a regular feature of late spring? Because there is a piece of physiological research that has been quietly published over the last 4 years, mostly in academic journals that the news cycle does not cover very often, and it has rewritten what we thought we knew about how much heat the human body can actually tolerate, and the answer is not the answer most people have been told. But before we get to that, we need to look at what was happening to the rest of Europe at the same time. because the British record was not a British story. It was a continental story. And the simultaneity of the pattern across half a dozen countries on the same calendar days is the second clue that what we are watching is something more structural than a single bad week of weather. Part 2. The map of a continent on fire. If you were to take a map of Europe at noon on Tuesday the 26th of May 2026 and colour in every weather station that had just broken its all-time May temperature record on that day or the day before, you would not be colouring in dots, you would be colouring in entire countries. The May 2026 event was not a British heat record. It was a Western European heat record, simultaneously, across at least 5 countries, at long-term stations that, like Kew Gardens, have been keeping data since the 19th century. Let me walk you through the numbers, because the geographic pattern is the part that turns this from a single national story into a continental one. Portugal set a new all-time national May temperature record on the 26th of May. The station at Moura, in the inland Alentejo region, recorded 40.3 degrees Celsius, that is 104.5 degrees Fahrenheit, in May. The station at Alviga recorded 40.1. 2 stations, both over 40 Celsius, both setting a new national May record on the same day. Portugal is no stranger to heat. It is a country whose summer climate routinely brings temperatures in the high 30s. But 40 Celsius is a number that, in Portuguese national climatology, has historically been a midsummer extreme, not a late spring measurement. Spain broke May records at more than 200 individual stations during the same one-week window. 200, not 2. Not 20. Over 200 individual weather observation sites simultaneously setting new monthly records. The Tortosa Observatory in Catalonia is one of the most reliable long-term records on the Iberian Peninsula. Its dataset goes back more than 100 years. The previous Tortosa May record was set in 2024, which itself was a noteworthy event at the time, at 36.1 degrees Celsius. The 2026 May reading at Tortosa was 37.3. Breaking a station record by over a degree in 2 consecutive years at a centennial site is the kind of pattern that climatologists track on multi-decade dashboards. 2024 broke it. 2026 broke 2024. The slope is what matters here, not just the single number. France experienced what Météo France, the official French weather service, described as unprecedented heat for the time of year. Monday the 25th in France was officially the country's hottest May day on record. Météo France is a careful agency. They do not use the word unprecedented casually. When their official communication on a record-breaking heat event opens with that word, the underlying data has moved past the polite vocabulary. Germany set new May records at multiple stations. So did Ireland. And in the broader Western and Central European temperature anomaly map for that week, the entire region, from the western coast of Ireland through the Iberian Peninsula, across France and Germany, into Central and parts of Eastern Europe, was running 10 to 15 degrees Celsius above the standard 1991 to 2020 climatological norm for that calendar position. 10 to 15 degrees above normal. That kind of anomaly, sustained for a week, is not a heatwave in the traditional sense. It is a different season. The atmosphere over Western Europe in late May 2026 was, for several consecutive days, behaving the way it should behave in July. Now, why is the simultaneity important? Why does it matter that all of these countries broke their records on roughly the same calendar week? The answer is that simultaneity is the signature of a hemispheric scale atmospheric pattern, not a regional fluke. If you have a record-breaking heat event in one country, it could be a local quirk, a particular configuration of low-level winds, a sea breeze that did not show up, a brief outbreak of dry air in the wrong place. When the same calendar week produces records at long-term stations across half a dozen countries all simultaneously, all under the same persistent ridge of high pressure, the explanation has to be at the level of the atmospheric pattern itself, not at the level of any individual country's geography. What climate scientists who study large-scale circulation will tell you is that the jet stream in late May 2026 was doing something specific. It was deeply amplified. Instead of running in a relatively zonal, that is west to east, pattern across the northern hemisphere, the jet was meandering. Big ridges, big troughs, big amplitudes, slow forward motion. The technical term for this is a high-amplitude Rossby wave pattern, and the slow forward motion is the part that does the damage. When the wave pattern locks, the ridges and the troughs stop moving. The high-pressure ridge over Western Europe in late May was not propagating eastward at the normal pace. It was anchored. This is the same physical phenomenon that has been showing up with increasing frequency across the Northern Hemisphere over the last 15 years. The Pacific Northwest heat dome of June 2021, the European heat waves of 2022 and 2023, the American Omega block of spring 2026 that the channel has been tracking for the last several weeks. The pattern is the same. A deeply meandered jet stream with large amplitude ridges and troughs that move slowly or not at all, parking persistent high-pressure systems over land for extended periods. And the bias toward this pattern showing up is not random. There is a peer-reviewed scientific literature that has been documenting the mechanism for over a decade. The proximate cause, as documented in research like the Kornhuber et al. 2020 paper in Nature Climate Change and the Hahn et al. 2021 paper in Water Resources Research, is something called quasi-resonant amplification of planetary scale waves, in plain English. The jet stream is driven, in part, by the temperature difference between the equator and the pole. A warmer equator and a colder pole produces a stronger, faster, more zonal jet. When the temperature difference shrinks, when the pole warms faster than the equator, the jet weakens, slows down, and starts to meander more. And the pole has, in fact, been warming much faster than the equator. The Rantanen et al. 2022 paper in Communications, Earth and Environment documented that the Arctic is warming approximately 4 times faster than the global average. So the equator to pole temperature gradient is shrinking, so the jet is slowing and meandering more. So slow-moving, high-amplitude ridge patterns are showing up more often, in places they did not used to show up, and they are staying put when they arrive. The May 2026 European event is one expression of that mechanism. It is not a freak. It is not unexplained. It is exactly the kind of event that the amplified planetary wave literature has been predicting we would see more of in regions like Western Europe during seasonal transition periods like late spring. The Met Office attribution result and the Rossby wave physics are telling the same story from 2 different angles. The dice have been weighted, and we now know which way they were weighted, and we know the mechanism for the weighting. The human cost of the event began arriving almost immediately. Across the United Kingdom alone, at least 12 people died in heat-related and water-related incidents during the event window. 9 of them were children. 3 of them were teenage boys who died in separate water rescues on the Wednesday and Thursday of the peak heat week, when the weather suddenly becomes uncomfortably hot in a country whose population is not acclimatized to heat, whose housing stock is built for a cold maritime climate, and whose summer recreational infrastructure includes a lot of rivers, canals, reservoirs, and quarry lakes. What people do is go into the water. And the water in Britain in late May is still very cold from the winter. The combination of high air temperatures, low water temperatures, and a population suddenly looking for relief is a known mortality pattern that British health authorities issue specific guidance about every year. In 2026, that pattern produced 12 confirmed deaths during this single event window. The UK Health Security Agency, the relevant public health body in England, escalated yellow heat health alerts to amber across most of the country on Friday, the 22nd of May, the day the heatwave began. Amber alerts remained in force across most of England for the duration of the peak heat. Hospitals reported elevated emergency department demand. Public transport experienced disruption. The water supply in parts of southeast England experienced strain. The kinds of secondary effects that British infrastructure has historically only seen during midsummer heat events were happening in late May, 3 weeks before the calendar even rolled over into June. We do not yet have the final UKHSA seasonal heat mortality estimate for May 2026. The agency releases summer season totals after the heat episodes have closed, and they fold individual events into a seasonal report later in the year. For context, the 2024 UK summer produced an estimated 1,311 heat-associated deaths. The 2025 summer produced an estimated 1,504. The May 2026 event has the structural ingredients of a season that is likely to sit at the upper end of that recent range or above it. We will have a number, officially, later this year. For now, the 12 confirmed water and heat-related fatalities are a lower bound, not a total. I want to give you one more piece of context for the British numbers, because the comparison with continental Europe sharpens the picture. The 2003 European heatwave killed over 70,000 people across the continent. Approximately 15,000 of those deaths were in France. In central Paris alone, during the worst weeks of August 2003, the death toll was around 735 excess mortalities. A formal attribution study published in 2016 by Daniel Mitchell and colleagues in the journal Environmental Research Letters found that approximately 506 of those Parisian deaths, about 69% of the total, were attributable to anthropogenic climate change. Of 735 summer deaths, the analysis estimated that approximately 506 would not have happened in a climate without human-caused warming. 506 people in one city, in one summer, 23 years ago, whose deaths were explicitly attributable to the additional warming the planet had accumulated by that point. The May 2026 event is, in many respects, structurally similar to the 2003 event. Same kind of slow-moving ridge, same kind of North African air mass advection, same kind of persistent high-amplitude wave pattern. The thing that differs is that 2026 is 23 years later, the baseline has continued to rise, and the events are now arriving earlier in the calendar than they did before. The picture across Europe in late May 2026 is what hemispheric scale, amplified jet stream patterns, produce when they park their ridges in the wrong places at the wrong times of year. It is what the peer-reviewed literature on quasi-resonant Rossby waves has been saying we should expect more of. It is what the long-term instrumental record at stations like Kew Gardens and Tortosa is now showing us in real time, and it is one of two simultaneous regional expressions of the larger atmospheric pattern that week. Because at the same time the European ridge was producing record-breaking heat across half a dozen countries, the other hemisphere of that same amplified jet stream was producing a different kind of heat, in a very different climate, in a country where the question of how much heat a human body can actually take is not a future question. It is a Tuesday afternoon. Part 3. The same week, on the other side of the hemisphere. If you fly 12 hours east from London, over the Mediterranean, over the eastern Mediterranean basin, over the Middle East, over Iran, over Pakistan, and into the great agricultural plains of northern India, you arrive in a place where the climate question we have been talking about looks very different. Where the British Met Office released a careful attribution note about a 35 degrees Celsius event in May, the Indian Meteorological Department issued orange alerts about a 47-degree event in May. Where 12 people in the United Kingdom died, mostly in water rescue scenarios, 16 people in the southern Indian state of Telangana alone died of heatstroke during the same calendar week. Where the British Prime Minister did not need to make a public statement about the weather, the Indian Prime Minister, Narendra Modi, made a public warning about the dangers of extreme heat. The same hemispheric atmospheric pattern, the same amplified jet stream, the same late May calendar position. Two different climate baselines, two different populations, two qualitatively different physiological situations. On Wednesday, the 21st of May, 2026, 4 days before the British record fell at Kew Gardens, the highest temperature anywhere on Earth, on that single day, was recorded at a city called Banda, in the state of Uttar Pradesh, in northern India. The reading was 47.6 degrees Celsius, that is 117.5 degrees Fahrenheit. The Indian Meteorological Department confirmed the measurement and circulated it as the global daily high. And there is a second statistic from that same midday that I want you to sit with for a moment, because it is the kind of number that does not get headlines, but tells you everything about what was happening on the ground. At midday on Wednesday, the 21st of May, the top 45 hottest cities anywhere on Earth, by recorded surface air temperature, were all in India. Every single one of them. All 45 of the hottest cities on the planet at that hour on that day were located within a single country. That is not a record. That is a structural statement about where heat was concentrated. Delhi, the Indian capital, had its warmest May night in 14 years. The Safdarjung observation station, which is the primary climatological reference station for the city, recorded a nighttime minimum of 31.9 degrees Celsius on the morning of the 21st. That is 5.2 degrees Celsius above the local May norm. The last time a Delhi May night had been warmer than that was the 26th of May, 2012, when the Safdarjung minimum touched 32.5. The daytime maximum at Safdarjung on the 21st was 43.6 degrees. Other parts of the Delhi metropolitan area touched or approached 45 degrees during the same period. The India Meteorological Department issued an orange level alert across Delhi and the surrounding national capital region, warning that maximum temperatures could touch 46 degrees Celsius in several Delhi districts during the heatwave window, and that the heatwave conditions would continue through Wednesday the 27th. I want to slow down on the nighttime number, the 31.9 degree minimum, because that is the kind of statistic that the public health literature pays much closer attention to than the daytime maximum. The human body recovers from heat overnight. Tissue temperature, especially in vulnerable populations, drops during the cooler hours of the early morning, and the body uses that recovery window to reset its thermoregulatory state. When the overnight low fails to drop below a particular threshold for multiple consecutive nights, cumulative core temperature stress builds. The body never gets to recover. The next day's heat compounds on a body that has not finished cooling from the previous day's heat. And in a city where a meaningful fraction of the population does not have access to active cooling, the death toll from a multi-day heatwave is largely driven by the nighttime minima, not the daytime maxima. A 31.9 degree nighttime low in Delhi means a city that did not drop below tropical mid-afternoon temperatures even in the deep early morning hours. That is the kind of nighttime signal that, in a humid environment, has historically been associated with the worst heat mortality events on record. The official confirmed heatstroke death toll for the week in the southern state of Telangana alone was at least 16. The Indian government routinely undercounts heat mortality because, unlike a country with a developed coroner system and a centralized public health reporting infrastructure, heatstroke deaths in much of India are attributed at the local hospital level and frequently get classified as cardiovascular events, or as natural causes, rather than as heat-related. The literature on Indian heat mortality, including the work of researchers like Dilip Mavalanka at the Indian Institute of Public Health, has been documenting this undercount for over a decade. The confirmed Telangana count of 16 is, almost certainly, a small fraction of the true heat mortality across India during that week. We do not have a verified all-India confirmed total. What we have are the state-level confirmed counts and the broader epidemiological literature that says the actual number is much higher than the official tallies suggest. I want to flag something specifically here, because a number was circulating during that week that I want you to ignore. There was a viral claim on social media that 50,000 people had died of heat in India during the week of the May 2026 event. That number is not verified. There is no Indian governmental source, no international agency source, no peer-reviewed estimate that supports the 50,000 figure. I'm not telling you that Indian heat mortality is small. I'm telling you that the 50,000 number is not the right number to anchor your understanding to. The confirmed Telangana count is 16 for the week. The likely true all-India number, given the documented undercount, is in the hundreds to low thousands range for that specific calendar week, and the seasonal Indian heat mortality estimates for years like 2015 and 2019 have run into the low thousands by year-end. Those are the verified numbers. The 50,000 claim was an inflated viral figure that did not survive contact with the official record. We can be appropriately concerned about Indian heat mortality using the real numbers. We do not need to use the inflated ones. The heatwave conditions were not confined to Delhi. The India Meteorological Department documented heatwave to severe heatwave conditions across at least 9 Indian states simultaneously during that week. The Vidarbha region, eastern and western Uttar Pradesh, eastern Madhya Pradesh, the Haryana-Chandigarh-Delhi corridor, Punjab, Uttarakhand, Chhattisgarh, and parts of Odisha. That is a geographic footprint covering hundreds of millions of people. The combined population of those administrative units is on the order of 450 million, roughly the population of the European Union. Concurrently experiencing heatwave to severe heatwave conditions, while the European Union itself was experiencing record-breaking heat in its own jurisdiction. The same calendar week, the same amplified jet stream pattern, the same large-scale circulation anomaly, just on opposite hemispheres of the same wave. The structural difference between the European event and the Indian event is the difference between dry heat and humid heat. Western Europe in late May 2026 was hot but relatively dry. The Saharan air mass that was being advected up over the continent had a hot continental origin, and the surface conditions across the affected European countries were characterized by low to moderate humidity. That is uncomfortable, and at 35 degrees Celsius it is dangerous, but the human body can still cool itself effectively through evaporation. Sweat evaporates well in dry air. The wet bulb temperature stays well below the cooling capacity threshold. Northern India, by contrast, is sitting on top of the Indo-Gangetic Plain, which in late May is approaching the pre-monsoon humidity loading from the Arabian Sea and the Bay of Bengal. The same kind of ridge over the same kind of land, with the same kind of 40+ degrees Celsius daytime maximum in northern India in late May, produces a much higher humidity loading and therefore a much higher wet bulb temperature than the same dry air event would in Europe. The body's ability to cool itself through sweat evaporation is much more constrained in the Indian setup than in the European one. This is the moment in the story where we have to talk about wet bulb temperature, because we are about to compare two heat waves that look superficially similar, both extreme, both record-breaking, both in late May, both driven by the same atmospheric pattern, and the physiological reality of what they do to the human body could not be more different. The European heat broke records but stayed comfortably within the limits of what an unacclimatized healthy adult can manage with shade, water, and minimal exertion. The Indian heat, for the most vulnerable segments of the population, almost certainly crossed the empirically established threshold beyond which the human body simply cannot cool itself, no matter how much shade, water, or rest is available. And that threshold is closer than science used to think it was, by about 4 degrees. Part 4. The number that used to mean survival. Let me ask you to picture something. Take a normal thermometer, the kind you remember from school, a glass tube with a mercury bulb at the bottom. Now take a small piece of cotton, a sock basically, and wrap it tightly around the bulb. Soak that sock in water until it is dripping. Now hold the thermometer up in a moving stream of air. What is going to happen? The water on the sock is going to evaporate, and as it evaporates, it is going to pull energy out of the bulb, because the phase change from liquid water to water vapor requires energy, and that energy has to come from somewhere. It comes from the bulb, so the bulb cools, the mercury contracts, the reading on the thermometer goes down. The drier the air around the sock, the more evaporation, the more cooling, the lower the reading. The more humid the air around the sock, the less evaporation, the less cooling, the higher the reading. At 100% humidity, saturated air, fog, a steam room, there is no evaporation, no cooling, and the reading on the wet thermometer equals the reading on a dry thermometer right next to it. That reading, the temperature you would get from a thermometer with a wet cotton bulb, sitting in moving air in a given environment, is what climate scientists and physiologists call the wet bulb temperature. And it is one of the most important numbers in the entire field of human heat physiology, because the wet bulb temperature is, in a precise physical sense, the lowest temperature to which evaporation can cool any object in that environment, including a human body. Here is why that matters. The human body, for almost all of its evolutionary history, has cooled itself the same way that wet bulb thermometer cools itself. Sweat is liquid water on the skin. When sweat evaporates, the phase change from liquid to vapor pulls energy out of the skin. That cooling effect at the surface draws heat out of the underlying tissue. As long as the air around the body is dry enough and cool enough that sweat can evaporate effectively, the body can hold its core temperature stable, even at very high air temperatures, just by sweating. This is why humans can run a marathon in 30-degree heat in Phoenix, where the air is dry, but a 5-kilometer walk in the same 30 degrees in a humid coastal climate can be life-threatening. The air temperature is the same, the wet bulb temperature is not. What the wet bulb temperature is really measuring is the cooling potential of the air. How much heat can the air absorb from an evaporating surface? How efficiently can a body shed metabolic heat into the surrounding environment? That cooling potential is the only thing standing between the body's metabolic rate, which is constantly producing internal heat as a byproduct of being alive, and a runaway rise in core body temperature that, at around 40.2 degrees Celsius, induces heat stroke and, beyond a relatively narrow range, induces death. The question that climate scientists started asking about 15 years ago was a simple one. Is there a wet bulb temperature so high that the body's evaporative cooling system simply cannot keep up? Is there a number where, no matter how much you sweat, no matter how much you drink, no matter how much shade you sit in, The air is so saturated that evaporation stops working and your core temperature starts to climb and cannot be brought back down without either a cooler environment or active mechanical cooling. The first major paper to attempt to answer that question was published in 2010 in the Proceedings of the National Academy of Sciences by Stephen Sherwood and Matthew Huber. The title was An Adaptability Limit to Climate Change Due to Heat Stress. Sherwood and Huber argued that, in principle, a sustained wet bulb temperature of 35 degrees Celsius for several hours would induce lethal hypothermia in an unprotected resting human. Their reasoning was that human skin temperature, under normal conditions, sits at approximately 35 degrees Celsius. Heat flows from hot to cold. As long as the air temperature is below 35 degrees, heat can flow out of the skin into the air, even before you factor in evaporative cooling. But if the wet bulb temperature reaches 35 degrees, then the maximum cooling effect of evaporation, which can only bring the skin down to the wet bulb temperature, no longer creates a temperature gradient that allows metabolic heat to escape. The body's core, which is constantly producing about 100 watts of heat just by being alive, cannot dump that heat into an environment that is already at the temperature of the body's surface. Core temperature climbs, hypothermia sets in. Without intervention, you die. The Sherwood and Huber paper put 35 degrees Celsius wet bulb on the climate science map as the theoretical upper limit of human survivability. The number became the most widely cited single statistic in the human heat and climate change literature for over a decade. Climate models started projecting where on Earth the 35-degree threshold might be crossed under various warming scenarios. The conclusion was reassuring, in a particular way. At the kind of warming we were heading toward, 2 degrees, 3 degrees, even 4 degrees of global mean temperature rise, the 35-degree wet bulb threshold would be crossed only in relatively narrow geographic regions, mostly around the Persian Gulf, parts of the Indus Valley, and during the absolute peaks of the most extreme heat waves. The 35-degree number became, in popular climate communication, the "we are not there yet" number. The number that said the truly catastrophic heat scenarios were still future scenarios, not present scenarios. There were 2 problems with that framing. The first problem was that Sherwood and Huber's 35-degree threshold was a theoretical upper bound. It was derived from first principles of heat transfer physics applied to an idealized model of a resting human body. It was not measured, it was calculated. The second problem was that the calculation assumed a particular set of conditions: a resting human, no clothing, no metabolic exertion beyond basal rate, perfect adaptation, that do not describe how most humans actually live. Most humans, in places where heat is most dangerous, are not resting in idealized conditions. They are working, they are walking, they are cooking, they are taking care of children, they are doing the activities of daily living, which generate metabolic heat above the basal rate. And in those conditions, the actual threshold of survivability is not the theoretical 35 degrees, it is much lower. Researchers at Pennsylvania State University, in a long-running program called the PSU HEAT Project for Human Environmental Age Thresholds, decided to actually measure where the threshold sits in real human subjects, performing real activities in controlled climate chambers where the temperature and humidity could be carefully manipulated and the subjects' physiological responses could be carefully monitored. The team was led by Daniel Vecellio, working with researchers including Tony Wolfe, Rachel Cottle, and W. Larry Kenny. The methodology was straightforward. Put a human subject in a climate chamber, have them perform a low-intensity activity equivalent to the metabolic demands of normal daily living, light walking, basic chores. Slowly increase the temperature and humidity in the chamber and monitor the subject's core body temperature in real time. Identify the environmental combination at which the subject's core temperature begins to rise uncontrollably. That is the point where evaporative cooling has stopped being sufficient. That is the actual physiological limit of compensability, sometimes called the limit of livability, because beyond that point, the body cannot maintain stable function indefinitely. When the results were published in the Journal of Applied Physiology in 2022, the paper had a title that should have triggered a much larger conversation than it did. The title was Evaluating the 35 degrees Celsius wet bulb temperature adaptability threshold for young, healthy subjects. And the conclusion, in plain English, was that the threshold is not 35 degrees. For young, healthy adults performing the metabolic demands of basic daily life, the actual measured threshold of uncompensable heat stress is approximately 31 degrees Celsius wet bulb, Not 35, 31, 4 full degrees Celsius lower than the long-standing theoretical number, 4 degrees lower than the threshold that had been driving climate model projections and public communication for over a decade. I want you to understand what that revision means. 4 degrees of wet bulb difference is enormous in terms of the actual range of conditions that exist in the real world. A 4-degree shift in the threshold dramatically expands the geographic regions and the heat event severities at which uncompensable heat is encountered. Conditions that, under the old 35-degree assumption, would have been characterized as extreme but survivable, turn out, under the empirical 31-degree threshold, to be already past the cooling capacity of healthy young adults performing light activity. Heat waves that the public has been told are dangerous but manageable in the regions where wet bulb loading runs high are actually crossing the empirical limit, and that is just for young, healthy adults. The follow-on research, which we will get to in a moment, found that for older adults and for people with cardiovascular or respiratory comorbidities, the threshold is lower still. There is one more clarifying point I want to make before we move on, because the units here can be confusing. When the PSU heat team measured a critical wet bulb temperature of 31 degrees Celsius, that does not translate to 31 degrees Celsius on a regular thermometer. The wet bulb is a combined measure of heat and humidity. A 31-degree wet bulb is what you get at approximately 40 degrees Celsius dry air with around 50% relative humidity, or approximately 35 degrees Celsius dry air with around 70% relative humidity, or approximately 32 degrees Celsius dry air with very high humidity, near 85 or 90%. Those are all conditions that occur in the real world on a regular basis, every year, in cities around the world. Cities in South Asia, in the Persian Gulf, in coastal Mexico, in parts of the southeastern United States during peak summer humidity events, in coastal areas of China and Southeast Asia. The 31-degree wet bulb threshold is not a future condition. It is a current condition that is encountered multiple times per year in dozens of populated regions on the planet. Part 5. What a Penn State lab found inside climate chambers. I want to spend a little more time on the PSU heat research because the findings extend well beyond the headline 31-degree number, and the broader picture they paint of human heat tolerance is what actually answers the question the Vecellio team was asking. The question was not just, is the Sherwood and Huber theoretical threshold accurate? The question was, what does heat tolerance actually look like across the range of human bodies and human activities that exist in the world? And the answer turned out to be that there is not one number. There is a range, and the range depends, in specific and important ways, on age, on activity level, and on the specific combination of dry temperature and humidity that produces the heat stress. The 2022 Vecellio paper was on young, healthy adults. The cohort was 18 to 34-year-olds in good cardiovascular health with no comorbidities. The empirical critical wet bulb temperature for that cohort, at modest activity equivalent to activities of daily living, was approximately 31 degrees. That was the youngest, healthiest, most heat-tolerant population the chamber methodology could test. And even at that population, the threshold was 4 degrees below the theoretical value. The follow-on work, in a series of papers culminating in a 2023 publication in the Proceedings of the National Academy of Sciences titled Greatly Enhanced Risk to Humans as a Consequence of Empirically Determined Lower Moist Heat Stress Tolerance, extended the methodology to older adults. The cohort for the older adult studies was ages 65 through 92. The result was sharper than the team had expected. Heat compensability curves, when plotted on a temperature-humidity chart, shifted leftward for older adults compared to young adults. The same combination of heat and humidity that produced compensable conditions for a 30-year-old produced uncompensable conditions for a 70-year-old. The mechanism was multifactorial. Older adults sweat less efficiently. Their cardiovascular systems respond to heat with less margin. Their skin blood flow regulation is impaired relative to younger adults. They have higher background rates of cardiovascular and respiratory comorbidities, coronary artery disease, congestive heart failure, chronic obstructive pulmonary disease, all of which are exacerbated by heat stress, and all of which reduce the body's reserve capacity for thermoregulation. The full range of empirically measured critical wet bulb temperatures across the PSU heat body of work, integrating across age and activity level, runs from approximately 19 degrees Celsius at the older adult, higher activity end of the spectrum, up to approximately 32 degrees Celsius at the young healthy adult, light activity end. 19 degrees Celsius wet bulb. Let me put that in the same translation terms I used a moment ago. A 19-degree wet bulb is what you get at approximately 46 degrees Celsius dry air with low humidity, or approximately 32 degrees Celsius dry air with high humidity, or somewhere in between depending on the specific humidity loading. Those are not exotic conditions. 46 degrees Celsius with low humidity is a summer afternoon in much of the Persian Gulf region. 32 degrees with high humidity is a summer afternoon in much of coastal South Asia, in coastal Mexico, in parts of Southeast Asia, in the Gulf Coast of the United States. For older adults performing the activities of daily living, climbing stairs, walking to a store, gardening, doing housework, the empirical compensability threshold is being crossed today in populated regions across the world every single summer. The PSU heat research also identified what happens after the threshold is crossed. The team observed that, above the critical environmental limit, the core body temperature that is associated with heat stroke, approximately 40.2 degrees Celsius, can be reached within 4 to 10 hours of sustained exposure. That is the operational window. From the moment a person crosses the empirical compensability threshold, the body has somewhere between 4 and 10 hours, depending on individual physiology and exact conditions, before it reaches the temperature at which heat stroke becomes likely. And heat stroke, once it sets in, has a mortality rate that ranges, depending on the medical response, from about 10% to over 50%. The window between uncomfortable and lethal is narrower than most people realize, and the threshold for entering that window is lower than science thought it was a decade ago. There is a third paper in the PSU heat body of work that I want to flag, because it answers a related question that the original Sherwood and Huber framing left ambiguous. The original framing was about whether a particular combination of heat and humidity is survivable in steady state. The Sherwood and Huber 35-degree number was, in essence, a long-term equilibrium threshold. The Vecellio empirical work measured the threshold for sustained activity over operationally relevant timescales, hours, not days. The implication is that the empirical threshold is the threshold that matters for the actual heatwave events that produce mortality in the real world. Heatwaves do not produce deaths because someone is exposed to the conditions for a week. They produce deaths because someone is exposed for the worst 4 to 10 hours of a single afternoon, often during an electrical grid failure that has removed their access to active cooling, and during those 4 to 10 hours their core body temperature climbs into the range that produces multi-organ failure. The empirical threshold is the operationally relevant threshold for that specific failure mode. There is one more piece of the wet bulb literature that I want to bring into the picture, because it answers the geographic question. The PSU heat studies established the physiological threshold. The question is then, where on earth is that threshold already being crossed, and how often? The work that addresses that question most directly is a paper by Colin Raymond and colleagues, published in Science Advances in 2020, titled The Emergence of Heat and Humidity Too Severe for Human Tolerance. Raymond and his co-authors analysed the global instrumental weather record from 1979 through 2017, looking for stations that had recorded wet bulb temperatures at or above various thresholds. The thresholds they looked at were the original Sherwood and Huber 35-degree value, the empirically lower thresholds from the emerging PSU heat literature, and intermediate values in between. The finding was direct. Even the original theoretical 35-degree wet bulb threshold had already been briefly crossed in the historical record at least a dozen times between 1979 and 2017. The locations were concentrated in 4 geographic regions: the coastline of the Persian Gulf, the Indus River Valley of Pakistan and northwestern India, the Red Sea coast, and parts of coastal Mexico. These were not future events. These were already documented. The theoretical "we are not there yet" threshold had, in fact, been there, briefly, multiple times, in specific locations where wet bulb loading combines extreme heat with extreme humidity from a nearby warm ocean source. The 35-degree number was not a future projection. It was a present condition sporadically in specific places. And the broader finding from Raymond's work was that the number of station observations approaching or exceeding the 30 degrees Celsius wet bulb mark already well into the uncompensable range for older adults under the PSU heat empirical framework, has approximately doubled worldwide since the start of the data window in 1979. That doubling has occurred over a window during which global mean surface temperature has risen by approximately 1 degree Celsius. The relationship between baseline warming and the frequency of extreme wet bulb exceedance is not linear. It is roughly exponential. A small increase in mean temperature in a region where the absolute humidity has also been rising because warmer air holds more moisture can produce a much larger increase in the frequency of extreme wet bulb events. That is the relationship that the geographic projection literature has been trying to quantify. So put these three pieces together. The theoretical 35-degree threshold from Sherwood and Huber, which was treated as the upper limit of human survivability for over a decade, has already been briefly crossed at least 12 times in specific places. The empirically measured threshold from the PSU heat chamber studies, which is the actually relevant threshold for composability during operational timescales, is approximately 4 degrees lower than the theoretical value for young healthy adults, and lower still for older adults. And the global frequency of station observations near the empirical thresholds has approximately doubled in the last 40 years, on a roughly exponential trajectory. The picture this paints is that we are not approaching the limits of human heat tolerance from a comfortable distance. We are sliding past them in specific places with a velocity that the public communication about heat has not yet caught up with. The next question we have to ask is what that means on the ground. Not in a paper, not in a model, in a real city with real infrastructure, real people, and a real heat wave that crosses the empirical threshold during an electrical grid failure. We have a historical data point for exactly that scenario. The data point is Karachi, Pakistan in June of 2015. That is the city, that is the year, and that is the event that, more than any other in modern record, shows what the wet bulb research is actually describing. Part 6. Karachi, 2015. The real-world test. Karachi is a city of around 20 million people, sitting on the Arabian Sea coast of southern Pakistan. In June of 2015, the city was hit by a heat wave that, even now, more than a decade later, sits as one of the most documented case studies in modern heat mortality science. The official confirmed death toll in Karachi alone was approximately 2,000 people, over a window of about 10 days. The broader Pakistani national death toll, including the surrounding Sindh province, was higher than that. Some estimates put the total above 2,500. The peak measured air temperature in the city, during the worst single day of the event, was 44.8 degrees Celsius. That is 112.6 degrees Fahrenheit. By the standards of the Indus Valley and the surrounding region, that is hot, but it is not historically unprecedented. Karachi has seen mid-40s Celsius temperatures before. What made the 2015 event different was not the peak dry temperature, it was the wet bulb loading. When you take a measured air temperature of 44.8 Celsius and combine it with the humidity that the Arabian Sea was advecting into the city during that week, you get a heat index, the apparent temperature, accounting for humidity, of approximately 66 degrees Celsius, 151 degrees Fahrenheit. The wet bulb globe temperature, which is a related but slightly different measure that incorporates radiant heat and wind in addition to temperature and humidity, exceeded 32.2 degrees Celsius during the day in Karachi during the peak event, and remained above 25.6 even at night. Those are conditions in which the human body, by every empirical standard the PSU heat research has since established, is operating very near or above its composability limit. The retrospective analyses applied to the Karachi 2015 data, using the empirical wet bulb thresholds developed in the years after the event, estimate that the event passed the uncompensable threshold for older adults for somewhere between 8 and 10% of its total duration. That is a small percentage of the elapsed time, but it represents the worst few hours of each peak afternoon, sustained across multiple consecutive days. The body count would have been bad even without the secondary factors, but two compounding circumstances turned a severe heat event into a mass casualty event. The first was the calendar. The heat wave overlapped with Ramadan. For approximately 1.8 billion Muslims worldwide, Ramadan is a month of religious observance during which adherents fast from dawn until sunset. No food, no water, for the entire daylight period. In southern Pakistan in mid-June, daylight runs about 14 hours. For approximately 14 hours per day, a substantial fraction of the Karachi population was not eating and not drinking, in air temperatures that, even before the heatwave, routinely climbed into the high 30s Celsius, and at humidity levels that made evaporative cooling much less effective than the dry temperature would suggest. The combination of fasting and extreme heat raises dehydration risk sharply. The body's sweating mechanism, which is the primary thermoregulatory tool, requires water. A dehydrated person produces less sweat, gets less evaporative cooling, and reaches the limit of compensability at a lower wet bulb temperature than a fully hydrated person. The Ramadan calendar overlap turned an event that would have killed hundreds into one that killed thousands. The second compounding factor was the grid. Pakistan's electrical infrastructure, at the time of the 2015 event, was already strained. Demand for electricity during a peak heat event in a city the size of Karachi is enormous. 20 million people, all running air conditioners or fans or refrigerators simultaneously, against the kind of demand profile that comes with extreme heat. The grid could not handle it. There were widespread power failures across the city, in many cases lasting 8, 10, 12 hours at a stretch. The failures removed exactly the equipment that vulnerable populations were depending on for survival. Air conditioners stopped working, ceiling fans stopped working, water pumps stopped working, meaning that, in addition to losing active cooling, people lost access to drinking water from municipal taps. Refrigeration of food and medication failed across whole neighbourhoods. The body count climbed sharply during the grid failure hours, particularly among elderly residents in low-income neighbourhoods who could not relocate to cooler environments and could not afford the petrol generators that wealthier households used as backup power. I want you to pause on what that meant operationally. The Karachi 2015 event was a heatwave whose human cost was driven not only by the meteorological conditions, but by the failure of the secondary infrastructure that the modern world has built specifically to allow human bodies to survive conditions like these. The air conditioning, the fans, the water pumps, the cold storage, the municipal water supply, all of it failed at the worst possible moment, and the people most harmed by the failure were the ones who had the fewest backup options. The elderly, the poor, the people living in housing without natural ventilation, the people whose medical conditions made them most heat vulnerable in the first place. Karachi in 2015 is, in the public health literature, the empirical answer to the question of what happens when a wet bulb threshold is briefly crossed in a city without functioning cooling infrastructure. The answer is 2,000 confirmed deaths in 10 days, and the actual number is almost certainly higher than that, given how undercounted heat-related mortality is in countries with limited coroner systems. The Karachi event matters for our discussion for two reasons. The first is that it is a real-world demonstration of the wet bulb thresholds. When the Vecellio team and others published their empirical critical environmental limits, the question naturally arose of what those numbers would actually mean in practice. Karachi 2015, retrospectively analysed using the empirical framework, is the answer. When a city of 20 million people crosses the older adult uncompensable threshold for 8 to 10% of a multi-day heat event, with grid failure removing active cooling for substantial portions of the worst hours, with a calendar that compounds dehydration risk, the result is mass casualty mortality at the scale of a major industrial accident or a small war. That is the operational reality of crossing the empirical threshold in a real population with real infrastructure constraints. There is a piece of the Karachi 2015 story that I want to add because it speaks to a question that comes up whenever people study mass mortality heat events. The question is whether, after an event like that, the affected region adapts, whether the lessons get internalised, whether the next heatwave produces fewer deaths, because the city has learned. The honest answer from the public health literature is mixed. Some cities have adapted dramatically after major heat disasters. Ahmedabad, in the Indian state of Gujarat, is the cleanest case study. After a 2010 heatwave killed over 1,500 people in the city, the Ahmedabad municipal authorities, working with public health researchers and community organisations, developed what came to be known as the Ahmedabad Heat Action Plan. The plan included heat health alert systems, public cooling centres, mandatory worker rest periods, training for community health workers, public awareness campaigns, and infrastructure investments in cool roofs and shade. The mortality outcome from subsequent heatwaves in Ahmedabad has been measurably lower than the trajectory the city was on before the plan was implemented. That is real adaptation, demonstrably effective, and it has been adopted as a model for over 30 other Indian cities and a number of cities outside India as well. Karachi has had a more difficult adaptation trajectory. Pakistan's general political and economic instability has limited the pace of large-scale public infrastructure investment. The grid has been upgraded in places, but not at the scale or pace required for the city's population growth and rising cooling demand. Heat action protocols have been adopted in principle, but inconsistently implemented in practice. The city has had additional heat waves since 2015, and the mortality from those events has been lower than from the original disaster, but not as low as a fully implemented Ahmedabad-style plan would predict. The difference between Ahmedabad's outcome and Karachi's outcome after similar magnitude initial events is not a difference in the meteorology. It is a difference in the political and economic capacity to translate the lessons of an event into coordinated public infrastructure response. The implication for the broader question we are asking in this video is that adaptation is real, but it is not automatic. It requires governance capacity, financial resources, technical expertise, and sustained political attention. Some cities have all of those things, many do not, and the geographic distribution of cities with versus without those capacities does not map cleanly onto the geographic distribution of heat exposure. Some of the most heat-exposed cities on the planet are also the cities with the most constrained adaptation capacity. The empirical wet bulb threshold does not care about governance capacity. The threshold is the threshold. The body cannot regulate above it. The question of how many people in a given city will die during the next event that crosses the threshold depends on the secondary factors: the cooling, the grid, the heat plan, the medical response, and those secondary factors are unevenly distributed in ways that the climate trajectory will magnify, not minimize, over the next several decades. The Karachi event also produced a body of public health research in the years after that has shaped how the field thinks about heat mortality in low and middle-income urban environments. The studies documented the demographic and spatial distribution of the deaths. The mortality was heavily concentrated in low-income neighborhoods, particularly in older buildings with poor ventilation, in residents over 65 years of age, in people with pre-existing cardiovascular and respiratory conditions, and in outdoor workers who could not relocate to cooler environments during the worst hours. The distribution maps almost exactly onto what the broader heat vulnerability literature predicts. The people who die in heat events are not randomly distributed across the population. They are the people whose age, income, health, and housing put them at the intersection of multiple risk factors at once. That intersection becomes deadly when the meteorological conditions cross the threshold and the secondary infrastructure that protects against the threshold fails simultaneously. The Karachi case is also, importantly, one of the most carefully documented cases of mortality at wet bulb conditions that did not formally exceed the original Sherwood and Huber 35-degree threshold. The wet bulb values during the worst hours of the worst days were elevated, but they did not reach the theoretical 35-degree number. They reached somewhere around 32 to 33, and 2,000 people died. That is the empirical data point that the Vecellio chamber studies were, in retrospect, calibrating against. The original theoretical threshold did not predict the Karachi mortality outcome. The lower empirical threshold does. The Karachi event is, in this sense, one of the strongest pieces of real-world evidence that the Sherwood and Huber theoretical number was too high, and that the actual physiological limit of compatibility is meaningfully lower than the discipline assumed for a decade. The bodies, in a sense, ran the experiment. The experiment said the threshold is lower than we thought. The second reason it matters is that the Karachi event is, in the climate projection literature, the prototype case study for what wet bulb crossings will look like in many more places, more often as warming continues. The Vecellio group and others have published forward modelling studies that take the Karachi 2015 event as a baseline and ask what the same atmospheric setup would produce in a climate warmed by an additional 1 degree, 2 degrees, or 3 degrees Celsius beyond the present baseline. The answers are sobering. At 2 degrees of additional warming above pre-industrial, which we are on track to reach in roughly 2 decades on current emissions trajectories, the same atmospheric event in Karachi would cross the uncompensable threshold for healthy young adults as well as older adults. The event that killed 2,000 mostly elderly people in 2015 would, in a 2-degree warmer climate, be killing across the full population age range. At 4 degrees of additional warming, the same event would be crossing the older adult threshold for approximately 90% of the heatwave's duration. Not the worst 8 to 10%, 90%. The exposure window would expand from the worst afternoon hours to virtually the entire event duration. The mortality outcome under those conditions, even with maximum operational intervention, would likely be an order of magnitude worse than 2015. I want to be careful with you about the certainty of those projections. Climate models have uncertainty. Heat mortality projections have additional uncertainty on top of the meteorological uncertainty because they have to make assumptions about future air conditioning penetration, grid reliability, public health response, urban planning adaptations, and a dozen other socio-economic variables that are not climate variables. The 2-degree projections for Karachi are not a forecast. They are a what-if. They are saying, if we hold all the secondary infrastructure conditions constant and we just modify the climate baseline by 2 degrees, this is what the empirical wet bulb thresholds tell us would happen to the same atmospheric event. That is a more modest claim than a forecast. It is a calibration of how sensitive the mortality outcome is to the underlying climate state. And the calibration tells us that the mortality outcome is very sensitive. A small shift in the climate produces a large shift in the body count. The 2,000 confirmed deaths in 2015, under the same meteorological conditions modified by a different climate baseline, becomes a much larger number very quickly. The Karachi case study is also a useful counter to a particular kind of complacency that crops up in conversations about heat and climate change. The complacency goes something like this. Yes, it gets hot in some places, but people adapt. They build air conditioning, they change their schedules, they drink more water. The mortality numbers will not actually get worse because humans are adaptable and the technology gets better and the public health response improves over time. That argument is not wrong exactly. People do adapt. Air conditioning penetration is rising in middle-income countries. Public health agencies are getting better at messaging during heat events. Heat action plans, of the kind that the city of Ahmedabad in India pioneered after a 2010 heat disaster, have demonstrably reduced heat mortality in cities that have implemented them. The argument is not nothing. But the Karachi 2015 event is the rebuttal to the strongest form of the argument. Even in a city with substantial air conditioning penetration, even with public health response active, even with the medical system trying its best, when the wet bulb threshold is crossed and the grid fails, the human body's structural relationship to its physical environment cannot be papered over with adaptation. The body is just a body. The threshold is just a threshold. And when the threshold is crossed without functioning cooling, the body cannot regulate. Adaptation has limits, and those limits are physiological, not technological. That brings us back by the most direct route to the May 2026 European event. The European event, despite the magnitude of the temperature records broken, did not cross the empirical wet bulb threshold for healthy adults. The European heat was relatively dry. The wet bulb values during the peak May 2026 days, even at the worst afternoon hours, stayed well below the 31-degree empirical compensability threshold. The heat was extreme, the records were broken, the mortality was real, but the cooling capacity of the human body was not, for the most part, overwhelmed. The Indian event, by contrast, on the same calendar week, in a more humid climate, almost certainly crossed the empirical threshold for vulnerable populations during the worst afternoon hours. The two events look superficially similar on a temperature map. Physiologically, they're completely different events. And the difference between them is the difference between a heat wave that breaks records and a heat wave that breaks bodies. The reason this distinction matters for understanding the future is that the structural pattern we are in is producing both kinds of events, simultaneously, with increasing frequency, on opposite hemispheres of the same amplified jet stream. The European ridge in May 2026 was a dry heat event. The Indian ridge the same week was a humid heat event, as the planetary atmospheric pattern continues to amplify and slow down, as the Arctic continues to warm faster than the equator, as the jet continues to meander more, as ridges continue to anchor for longer in places where they used to move through, we're going to see more of both kinds of events. The dry heat events will keep breaking temperature records in places like Britain and Western Europe. The humid heat events will keep crossing wet bulb thresholds in places like northern India, the Persian Gulf, coastal Mexico, the Gulf Coast of the United States. And the question of how much of the global population is exposed to the more dangerous category of heat event, the kind that crosses the empirical compensability threshold, is the question that the geographic projection literature has been trying to quantify. Part 7. The map at 2 degrees. In 2023, a paper appeared in Nature Communications titled A Physiological Approach for Assessing Human Survivability and Livability to Heat in a Changing Climate by Lou and Romps. The paper applied the empirical PSU heat critical environmental limits to global climate model output and produced what is probably the most carefully constructed projection currently available of where on Earth the human body's cooling threshold is at risk under different levels of additional warming. The projections in that paper and in the related Vicelio team work are what we have to talk about now, because once you accept the empirical thresholds and you apply them to the geographic distribution of where humans actually live, the map you produce is not a map most people have seen. Here is what the map looks like at 2 degrees Celsius of additional global mean warming above the pre-industrial baseline. Approximately 35% of Earth's land area becomes vulnerable to uncompensable heat events during peak heat waves at that level of warming. 35% of the world's land surface. That is the headline number. But the headline number, by itself, can sound abstract. The part that brings the picture into focus is which 35%. The 2-degree projection at the geographic level affects most of populated India, almost the entirety of the Gangetic Plain, most of populated eastern China, the Great East Coast Economic Corridor from Beijing south through Shanghai and Guangzhou, most of populated Southeast Asia, Bangladesh, the Mekong Delta, much of Indonesia, much of the Philippines, large parts of West Africa, Nigeria, Ghana, the coastal countries of the Gulf of Guinea, parts of South America, much of the Brazilian Amazon basin and the lower Paraná River basin, significant parts of Central America and coastal Mexico, and, critically for an American audience, much of the eastern half of the United States, the Mississippi Valley, the Gulf Coast, the Florida Peninsula, the lower Atlantic seaboard, large parts of the Carolinas, Georgia, Alabama, Louisiana, eastern Texas, the American Midwest during peak summer humidity events. New York City, Philadelphia, Washington, and Boston are not exempt. The humidity loading along the eastern seaboard during August heat events already produces wet bulb temperatures that, at 2 degrees of additional warming, will cross the empirical compensability threshold for vulnerable populations during peak afternoons. 2 degrees of additional warming is not a distant scenario. The current global mean surface temperature is somewhere between 1.3 and 1.5 degrees Celsius above the late 19th century baseline, depending on which dataset and which reference period you use. We are roughly half a degree away from the 2-degree threshold. At current emissions trajectories, that is, at the actual policy trajectory the world is operating on, not the most aggressive mitigation scenarios and not the most pessimistic do-nothing scenarios, global mean temperature is projected to reach 2 degrees above pre-industrial somewhere in the late 2030s or early 2040s, roughly 2 decades from now. The current 20-year-olds will be in their early 40s. The current 40-year-olds will be in their 60s. So the geographic projection at 2 degrees of warming is not a problem for a distant generation. It is a problem for the current adult workforce during their working careers, and the populations who will be living, working, raising children, and growing old inside the 35% of Earth's land area that becomes vulnerable to uncompensable heat events at that warming threshold include, by current projections, well over half of humanity. Most of the populations of India, China, and Southeast Asia. Most of the populations of the Gulf states, of coastal North Africa, of West Africa. Substantial portions of the United States, of Latin America, of Southern Europe. The number of people who will be living inside the affected geographic envelope at 2 degrees of warming is, conservatively, 3 to 4 billion. The number of people who, during peak heat events in their region, will be crossing the empirical compensability threshold for the most vulnerable segments of their population, the elderly, the very young, the immunocompromised, the chronically ill, the outdoor workers, is conservatively in the hundreds of millions to over 1 billion. I want to flag the 4-degree projection, briefly, because it is in the same scientific paper, and the contrast between the 2-degree map and the 4-degree map is informative. At 4 degrees of additional warming, the projected geographic envelope of vulnerability expands from 35% of Earth's land area to over 60%. The affected regions extend well into northern Europe, into substantial parts of the Russian heartland, into much of central and northern China, into the entirety of the Indian subcontinent, into virtually the entirety of Southeast Asia, into the upper Midwest of the United States and the southern provinces of Canada. The 4-degree projection is not the current policy trajectory. It is the upper end of the plausible warming range under continued business as usual without major mitigation action. Whether we get to 4 degrees depends on policy choices that have not yet been made and on climate sensitivity feedbacks that are still uncertain. The 2-degree projection is what we are on the road to. The 4-degree projection is what we get if the road does not change course. The difference between 2 degrees and 4 degrees, in terms of the geographic envelope of populations exposed to uncompensable heat, is the difference between about a third of Earth's land area and well over half. That is the spread that is on the table during the next 20 to 50 years. There is one more comparative projection I want to bring in here, because it pins the human cost in a place we have already discussed. Independent attribution work has projected what the 2003 European heatwave, the one that killed 70,000 people across the continent and 15,000 in France, would look like in a 2-degree warmer climate. The result is that 2003 magnitude heatwaves in central France are projected to become events expected once every few years rather than once a century. Once a century becomes once every 3 to 5 years, and the next iteration of those events, against a hotter European baseline with continuing pattern amplification, will not be limited to the magnitude of the 2003 event. They will be hotter than the original. The mortality risk that European public health systems built up to address after the 2003 disaster was calibrated for events with a 100-year return period. Recalibrating the public health system for events with a 3 to 5-year return period, at higher magnitudes, is a different order of magnitude of preparation than what is currently in place. The structural picture, when you put the 2-degree projection together with the empirical wet bulb research and the historical Karachi anchor and the current May 2026 European and Indian events, is this. We are not facing a future heat problem. We are facing a present heat problem that is set to expand its geographic footprint by an order of magnitude over the next 2 decades. The empirical cooling limit of the human body is closer than science thought a decade ago. The geographic envelope of populations exposed to that limit during peak events is expanding into the most heavily populated regions of the planet. And the time horizon for the expansion is the working careers of people currently in their 20s. That is the structural picture. The question, then, is what can be done about it. And the most obvious answer is also the answer that, on closer inspection, has its own structural problems. Part 8. The cooling paradox. If the human body cannot cool itself, in environments above the empirical wet bulb threshold, without help, then the obvious solution is to provide the help. Cool the environment around the body, get the wet bulb temperature in the room down below the threshold. Use mechanical refrigeration, an air conditioner, a vapor compression cycle running on electricity to extract heat from indoor air and dump it outside. The technology exists. It has existed for over a century. It is, in most rich countries, already ubiquitous. The problem is not, primarily, that we do not have the technology. The problem is that the technology, deployed as the dominant adaptation strategy, runs into 3 structural problems simultaneously. It is unequally accessible to the populations who need it most. It is grid-dependent at exactly the times when the grid is most vulnerable. And it is itself a major contributor to the emissions driving the underlying problem. Let me walk through each of those, because the 3 together describe what people in this field have started calling the cooling paradox. The first structural problem is access. Air conditioning on a global basis is unequally distributed in ways that map almost exactly onto income. The International Energy Agency has been tracking this for years. Approximately 3.5 billion people currently live in regions with high heat exposure, the kind of regions where peak summer wet bulb loading routinely approaches or exceeds the empirical compensability thresholds. Of those 3.5 billion people, only about 15% currently own an air conditioner. The other 85%, when their region has a heat wave, are managing with fans, with cross-ventilation, with cool roofs, with shade trees, with relocation to commercial buildings that have cooling, with the kinds of behavioral adaptations that humans have used for thousands of years before mechanical refrigeration existed. And those adaptations work, up to a point. They do not work when the wet bulb threshold is crossed. The body does not care what neighborhood you live in. The threshold is the threshold. Within the regions where air conditioning is most needed, ownership is heavily concentrated in higher-income households. In East Asia and the Pacific, a region that includes both wealthy countries like Japan and Singapore and lower middle-income countries like Indonesia, the Philippines and Vietnam, air conditioning ownership in the lowest income quartile is approximately 25%. In the highest income quartile of the same region, it is over 75%. The same pattern holds in much of South Asia, in much of the Middle East, in much of Latin America. The people who are statistically most heat exposed, older adults in low-income urban neighbourhoods, workers in informal housing, residents of poorly ventilated apartment blocks, are the people least likely to have access to active cooling during the events that most threaten their lives. The Karachi 2015 mortality distribution is the worked example of what that geographic pattern produces. The projection from Sustainable Energy for All and from the IEA is that by 2050, approximately 2.5 billion people in hot countries will own air conditioning, up from the roughly 500 million who own it today. That is real progress. It represents a 5-fold expansion of cooling access in the most exposed regions over a quarter century. But the same projection, in the same window, has approximately 1.9 billion people in hot countries still without air conditioning. The growth in access is large in absolute terms and inadequate in relative terms. Even under the most optimistic deployment trajectories, somewhere around half of the population in hot regions will not have active cooling in their homes during the events that will most threaten their lives. That gap is not a small problem to be papered over. It is a fundamental constraint on what air conditioning, as an adaptation strategy, can actually accomplish at the global scale. The second structural problem is grid dependence. Air conditioning runs on electricity. Electricity comes from the grid. The grid, in essentially every country that has substantial air conditioning penetration, is at peak demand precisely during the hottest weather. Hot days are the days when everyone is running their cooling simultaneously. The grid load profile in places like Texas, California, Arizona, much of India, much of China, much of southern Europe is a roughly bimodal curve, with a sharp afternoon peak that tracks the daily temperature peak. The grid has to be built to handle that peak demand or it has to fail. In recent years, particularly in the United States, the failure mode has been increasingly visible. Climate Central, which tracks heat-related power outages in the United States, has documented that the rate of heat season power outages in the country has increased by approximately 60% over the last decade compared to the first decade of their data series. That is a sharp acceleration. The combination of aging grid infrastructure, rising peak demand, and the failure mode of high-voltage transformers under sustained heat is producing an environment in which the grid is becoming less reliable, precisely as our dependence on it for survival is increasing. The places most affected are not the places you would predict from population alone. They are the places where summer temperatures are climbing fastest, and the grid infrastructure is most strained. Texas, California, Arizona, Nevada, much of the southeastern United States. Modelling work projects that those 4 states are facing more than 4 months per year of temperatures sufficient to compromise transformer reliability under current trajectories. And the Karachi 2015 example is, again, the empirical anchor for what happens when the grid fails during a heat wave that has already crossed compensability. The cooling that the wealthier residents depended on stopped working. The vulnerable populations who depended on functioning air conditioning, fans, water pumps and refrigeration lost all of it simultaneously during the worst hours of the worst days in temperatures that exceeded the body's compensability threshold for older adults. The grid failure was not a meteorological event, it was an infrastructure event, but it converted a serious heat event into a mass mortality event, because the secondary system that the population was depending on to keep them on the survivable side of the wet bulb threshold stopped working at the same time as the meteorological conditions pushed them past it. That is the operational vulnerability that the cooling paradox describes. The system that protects you is the system that fails during the conditions you need protection from. The third structural problem is the climate feedback. Air conditioning, deployed at the scale required to provide cooling to billions of people during increasingly frequent and intense heat events, is itself a significant source of greenhouse gas emissions. The emissions come from 2 sources. The first is the electricity that runs the units, which in countries where the grid is still substantially fossil fuel-based, produces carbon dioxide emissions in proportion to cooling demand. The second is the refrigerants, the working fluids inside the units, which are mostly hydrofluorocarbons, a class of synthetic chemicals with global warming potentials hundreds to thousands of times higher than carbon dioxide on a per-molecule basis. Refrigerant leakage from air conditioning systems, over their operational lifetime, contributes a significant fraction of the global warming impact of the cooling sector. The numbers, from the International Energy Agency and from Our World in Data, are that air conditioning currently accounts for somewhere between 3 and 7% of global greenhouse gas emissions, depending on accounting methodology and which sources are included. The IEA's Future of Cooling report projected that, under business as usual without significant policy intervention, the global stock of air conditioners in buildings is set to grow from approximately 1.6 billion units today to approximately 5.6 billion by 2050. The global energy demand from cooling is projected to triple over the same window, requiring new electricity capacity roughly equivalent to the combined current electricity capacity of the United States, the European Union, and Japan. Greenhouse gas emissions from cooling could double by 2030 and triple by 2050, reaching roughly 1,300 million tons of carbon dioxide equivalent annually. The proportional share of global emissions from cooling could reach approximately 10% by 2050. That last set of numbers is the part that produces the paradox. We need air conditioning urgently to allow vulnerable populations to survive the heat events that are coming. The geographic expansion of air conditioning access is one of the most critical adaptation measures we can deploy, but deploying it at the scale and on the timeline that the heat exposure projection requires, in a world that is still substantially fossil fuel powered, drives global emissions in exactly the wrong direction. The adaptation strategy that protects bodies from the symptoms of warming is itself a contributor to the warming, and the contribution is not trivial. It is on the order of 10% of global emissions by mid-century, in a world where every percent of remaining emissions matters for keeping the warming trajectory near 2 degrees rather than 3 or 4. The way out of the paradox in principle is not complicated. The energy that runs the air conditioning has to come from sources that do not emit greenhouse gases: solar, wind, nuclear, hydro, geothermal. A global electricity grid powered by zero-emission sources removes the climate feedback from the cooling equation. The refrigerants have to be replaced with lower global warming potential alternatives, which is already happening under the Kigali Amendment to the Montreal Protocol. The cooling units themselves have to become more efficient, which is a continuous engineering challenge but a tractable one. None of these solutions are mysterious. The IEA's efficient cooling scenario, in the same Future of Cooling report, lays out a trajectory under which improved efficiency and clean energy could roughly halve the projected emissions growth from cooling. The technology exists. The deployment timeline is what is uncertain. But even with the most aggressive clean energy and efficiency deployment, the other two structural problems, access inequality and grid reliability, do not go away. A solar-powered air conditioner is still an air conditioner. It still requires upfront capital, which low-income households frequently do not have. It still requires a working grid connection during peak demand, which the most vulnerable neighborhoods frequently lack. It still requires shelter that is physically sealed enough to retain cooled air, which much of the world's informal housing stock is not. Cleaner power and more efficient units improve the emissions math. They do not solve the cooling poverty problem, and they do not solve the grid fragility problem. The paradox is structural, not just emission structural, and the engineering response to it has to address all three of its faces simultaneously. What the wider literature is suggesting increasingly is that air conditioning has to be the central element of a much broader adaptation strategy that includes urban design changes, building envelope improvements, public cooling infrastructure, grid hardening, behavioral adaptations, and emergency response protocols, cool roofs, green roofs, reflective pavement, urban tree canopy expansion, building codes that require insulation and shading, public cooling centres that vulnerable populations can reach during heat events, heat action plans of the kind that Ahmedabad, India pioneered after the 2010 event, which have demonstrably reduced heat mortality in cities that have implemented them, mandatory rest periods for outdoor workers during peak heat hours, heat health alert systems that get vulnerable populations into shelter before the threshold is crossed. None of those are substitutes for air conditioning. All of them are necessary complements to it. The picture that emerges when you look at the operational adaptation literature seriously is that the cooling paradox does not have a single solution. It has a dozen partial solutions, all of which have to be deployed in parallel on a timeline that is much shorter than the development pace that most public infrastructure operates on. That is the operational picture, as honestly as I can convey it to you. The technology exists, the deployment is happening, and the deployment is not happening fast enough to keep up with the rate at which the empirical envelope of human heat tolerance is being squeezed by the rate at which the climate is changing. The question of whether the gap between adaptation and warming can be closed, on the timescale that matters, is one of the central operational questions in climate policy right now. And the May 2026 European event, for all its specific national records and its specific national mortality, is the most recent piece of evidence on the table for what the gap currently looks like. Part 9. The question scientists are now asking out loud. So let me bring this back to where we started, to the small instrumental station on the south bank of the Thames, to the thermometer that, on Monday the 25th of May, 2026, read 34.8 degrees Celsius, and the next day read 35.1, to the 80-year-old record that fell by more than 2 degrees on consecutive days, to the senior climate scientist at Maynooth University who used the phrase mind-bogglingly crazy on CNN, to the British Met Office in a peer-reviewed journal of the Royal Meteorological Society, formally stating that breaking that record is now 3 times more likely than it was in a climate without anthropogenic forcing, and to the question that the wet bulb research has been quietly setting up for the better part of 2 decades, that the Sherwood and Huber paper articulated as a theoretical limit 15 years ago, that the Vecellio team revised downward to an empirical threshold 4 years ago, that the Lew and Romp's geographic projection mapped onto a population 3 years ago, and that the May 2026 European event has just brought to the surface of the public conversation in a way it has not been before. The question is this: if the British climate, which is the most ocean-moderated and historically temperate climate of any major European nation, can in late May post a temperature that no June in nearly 50 years has matched at the same station, and if the empirical cooling limit of the human body is approximately 4 degrees Celsius lower than science thought a decade ago, and if the geographic envelope of populations exposed to uncompensable heat events at 2 degrees of warming is expanding to include most of the populated regions of India, eastern China, the eastern United States, and much of Southeast Asia, and if 2 degrees of warming is approximately 2 decades away on the current policy trajectory, then the question on the table is not whether the climate is changing. The climate is changing. That is the data. The question on the table is whether the structural relationship between the human body and the climate it lives inside is changing fast enough that adaptation is even possible at the speed the atmosphere is moving. That is the question. And I want to be honest with you about it because the honest version of the question is also the version that is not yet fully on the public record in most outlets. The public discussion of climate change for most of the last 30 years has been framed in terms of damages and dollars. The economic cost of sea level rise, the agricultural cost of changing growing seasons, the infrastructure cost of more frequent flooding, the insurance cost of more intense storms, those are real costs and they matter, and they have driven most of the policy conversation. But the wet bulb research has introduced a different kind of variable into the conversation that does not translate cleanly into dollars. It is the variable of physiological compatibility, whether the populations of the regions where most humans currently live will be able, on the trajectory we are on, to continue living in those regions through the working careers of people currently in their 20s. Not just whether they will be poorer or hotter or more frequently displaced by storms. Whether the actual structural relationship between a body and a climate in the most populated parts of the planet can be maintained with technology on the timescale the trajectory implies. The answer that the wet bulb research is starting to suggest, with caveats and uncertainties and the careful epistemic humility that good science requires, is that the answer is not clear. The 2-degree projection at the geographic level puts a third of Earth's land area inside the vulnerability envelope. The 4-degree projection puts almost 2/3. The adaptation tool we are most relying on, active mechanical cooling, runs into 3 structural problems simultaneously, and the engineering response to those problems is on a deployment timeline that may not be short enough. The Karachi 2015 event is the empirical anchor for what happens when the threshold is crossed and the adaptation system fails simultaneously, and the projection for the same event at a hotter baseline is an order of magnitude worse. The May 2026 European event was not, on its own, the kind of event that crosses the threshold for healthy adults. The simultaneous Indian event almost certainly did, for the most vulnerable populations during the worst hours. Both events came from the same amplified atmospheric pattern on the same calendar week in the same year. Both events are consistent with the pattern that the planetary wave literature has been describing for over a decade, and both events are the most recent in a sequence that has been accelerating, with each year producing new records in new places at new times of year. I want to tell you what I think the honest framing of all of this is, because the data is what it is, and the implication is what it is, and the question is what it is, but the framing matters for how we hold all of it. The framing is not that we are doomed. That is the thumbnail question, and the thumbnail is doing what thumbnails do. It is asking the question with the maximum stakes attached so that you click. But the actual scientific answer to "are we doomed" is more nuanced than the thumbnail allows. The wet bulb research describes a real physiological threshold that is being approached in real places under realistic climate trajectories. The geographic projection describes a real expansion of vulnerability over a real-time horizon. The cooling paradox describes real structural problems with the adaptation strategy we are most relying on. But none of those individual pieces, even in combination, add up to a deterministic forecast that humanity, as a whole, cannot inhabit the planet during the next century. They add up to a forecast that the inhabitation will require, on a much shorter timescale than the public discussion has been operating on, a much more aggressive and coordinated set of adaptation measures than is currently being deployed. The question is not whether we are doomed. The question is whether we are moving fast enough to avoid the parts of the trajectory that would make particular regions, for particular populations, on particular timescales, structurally unsurvivable in the absence of working active cooling. That is the question that senior climate scientists in the wake of the May 2026 European records are starting to ask out loud in a way they were not asking 5 years ago. Not because the science is new. Most of the science has been on the table for years, but because the events are arriving earlier and harder than the science had projected, and because the empirical thresholds have come in lower than the theoretical thresholds had estimated, and because the cooling paradox has not, despite a decade of policy attention, been resolved. The pace of the climate is exceeding the pace of the adaptation. The pace of the events is exceeding the pace of the public communication about them. And the pace at which the question is becoming operational is exceeding the pace at which the political conversation has been processing it. I want to give you one more piece of context, because the picture I have painted in this video is necessarily focused on the data, and the data is uncomfortable, and I do not want to leave you with the impression that nothing is being done and that the situation is fully bleak. The actual operational reality is that significant adaptation work is happening in many places, and the trajectory of that work, while not fast enough to fully resolve the cooling paradox or to fully outpace the climate trajectory, is not nothing. Heat action plans of the kind that Ahmedabad pioneered have been adopted in dozens of cities across India, in cities across the Middle East and Southeast Asia, and increasingly in cities in Europe and North America. The Phoenix, Arizona Heat Plan, the Miami-Dade Heat Plan, the Chicago Heat Plan after the 1995 disaster. All of these are real, operationally deployed public health responses that have reduced mortality from individual events relative to the trajectory those cities would have been on without the plans. The European response after the 2003 event included substantial public health system changes, heat health alert systems, mandatory monitoring of elderly residents in care facilities during heat events, public cooling centres, public awareness campaigns. The British Met Office Heat Health Alert System, which was activated in May 2026 and likely saved lives during the event we have been discussing, did not exist in 2003. The alert escalation from yellow to amber on the 22nd of May was, in operational terms, the system working as designed. Air conditioning deployment is, despite the inequities, expanding rapidly in the regions where it is most needed. The IEA projection of 1.6 billion units today, growing to 5.6 billion by 2050, represents a real and unprecedented expansion of cooling access. Cleaner electricity is, in many countries, deploying faster than the IEA business as usual scenarios assumed 5 years ago. Solar and wind capacity has been growing at compound annual rates that exceed the projections from the early 2020s. Some of the underlying assumptions of the cooling paradox, that the electricity running the air conditioning will continue to be predominantly fossil-fueled may be less true in 2040 than they appear today, depending on the trajectory of clean energy deployment. The math of the paradox can be improved, in principle, by improving the energy mix and the efficiency of the units. Building codes are changing. Cool roof regulations are being adopted. Urban tree canopy expansion programs are operational in many cities. Reflective pavement is being deployed in pilot programs. Public cooling center networks are expanding. The cumulative effect of these measures deployed at scale is a real reduction in urban heat island effects, and a real expansion of cooling capacity that is available to vulnerable populations. None of this is sufficient to fully close the gap between the climate trajectory and the adaptation requirement, but it is also not nothing. Honest framing requires acknowledging both the gap and the work being done to close it. The honest framing is that we are in a race. The climate trajectory is one runner. The adaptation deployment is another runner. The empirical wet bulb threshold is the finish line. The race is happening in real time, in the working careers of people watching this video. The outcome depends on which runner moves faster, and the speed of both runners is, to a significant extent, under human control. The climate trajectory can be slowed by reducing emissions. The adaptation deployment can be accelerated by directing investment and policy attention to it. Neither variable is fixed. Both are decisions, made by societies and governments, with consequences that are measurable, traceable, and reportable. The Kew Gardens reading on the 26th of May 2026 is a data point in that race. It is telling us how fast the climate runner is currently moving. The empirical thresholds tell us how close we are to the finish line. The cooling paradox describes the challenges the adaptation runner faces. The May 2026 event is one of the most direct contemporary measurements of where the race currently stands. And the question Peter Thorne and his colleagues are asking, with phrases like mind-bogglingly crazy in mainstream media outlets, is the question of whether the adaptation runner can be sped up enough on the timescale that matters to keep the outcome from being determined by the climate runner alone. That is the operational version of the question. The thumbnail asks if we're doomed. The operational version asks what it would actually take, in policy terms and investment terms and social mobilization terms, to close the gap between the climate trajectory and the adaptation capacity on the timescale that the empirical thresholds require. The answer to the thumbnail question, with respect to humanity as a whole, is almost certainly no. The species is adaptable. The technology exists. The trajectory can be modified. The answer to the operational question, with respect to specific regions and specific populations and specific generations, is more contingent. Some places will adapt in time. Some places, on current trajectories, may not. The May 2026 European event has placed that distinction on the table, and it has done so with the kind of magnitude and simultaneity and physiological context that earlier events have not. The question is not whether we are doomed. The question is what we choose to do now that the data is in front of us before the next event arrives. When the thermometer at Kew Gardens read 35.1 degrees Celsius on the 26th of May, 2026, what it was reading was not just a temperature, it was reading a position on a trajectory. The trajectory is real. The slope of the trajectory is documented. The geographic and physiological implications of the trajectory are being worked out, one peer-reviewed paper at a time, in fields that have been doing this carefully for decades. The most recent measurements at Kew Gardens, the simultaneous records across Western Europe, the same week's events in India, the Karachi 2015 anchor, the empirical wet bulb thresholds, and the 2-degree geographic projection are all data points on the same curve. The curve is going up. The question is how fast it is going up relative to how fast we can respond. And the people who study this for a living, who have been studying it for a long time, who use careful language in peer-reviewed journals as their daily professional standard, are starting to use language outside that standard. Mind-bogglingly crazy is not the language of normal climate communication. It is the language of a scientist who has just watched a record at one of the oldest weather stations in his region fall by more than 2 degrees on 2 consecutive days, in late spring, in a maritime temperate climate that was never supposed to do that. It is the language of someone who is in real time recalibrating his sense of what the climate system can produce, in the country he lives in, on the calendar he lives on. And if Peter Thorne, at the Icarus Climate Research Centre, is recalibrating, then the rest of us probably should be too. Not toward despair, not toward fatalism, toward attention, toward urgency, toward asking the harder version of the question with the empirical thresholds in front of us, and the geographic projections in front of us, and the cooling paradox in front of us, and the realization that the working careers of people currently in their 20s are going to be the careers in which this question is answered one way or the other. The thermometer at Kew Gardens will keep reading whatever is in front of it. The atmosphere will keep doing whatever the physics tells it to do. The bodies of the people living in the affected regions will keep responding, or failing to respond, exactly the way human bodies have always responded to heat. The variable that is up for grabs is the variable of how fast humans, as a species and as a set of overlapping societies, respond to the data that the thermometer and the climate models and the chamber studies and the geographic projections have been delivering in plain and increasingly urgent language for a decade. Whether the response is fast enough is the question that the May 2026 event has placed back on the table in front of all of us in a way that is harder to dismiss than the previous version was. Whether we get to the answer in time depends on what we do with the question now that it is in front of us, and that, more than the records broken, more than the mortality counts, more than the headlines, more than the quotes from senior scientists about how crazy the data has become, that is what the May 2026 European heatwave is actually telling us. Not just what happened, not just what the numbers were, but what the question is now that the data is on the table, and what we choose to do with it.